Okay, welcome everyone to this presentation entitled Bridge Accelerator. We want to speak about Adam's Bridge Accelerator that can bridge the gap between existing asymmetric public key cryptography with post-quantum cryptography. My name is Moshtaba Bishaniyasar, and I'm here on behalf of my colleagues, Bharat and Bryan from Microsoft. So let's start with the introduction. The public key cryptography is required to generate a shared secret key between two parties that wants to communicate against unsecured channels such as the internet. And these actually public key cryptography that we have already, RSA and ECC, are based on some mathematical problems, factorization large integers and discrete logarithms. And these problems can be solved when we have a large scale of the quantum computers. So based on that, we need to develop a new framework, a new problem to protect our communication against quantum computers. So we call this new framework post-quantum cryptography. And we have to immigrate to the post-quantum cryptography to protect all of our communication, all of our system against both classical computers and quantum computers. There are several different approaches to design a post-quantum crypto system, and one of the most promising approach is lattices from the efficiency, performance, and side channel point of view, and specifically key size. So based on this need, PQC NIST started a PQC standardization process from 2016 with 69 different candidates. And after several rounds, they have selected some initial schemes to be standardized in 2022. And last year, in 2023, they published the first draft of the standardization. And hopefully, we have the final standardization in a few months this year. So you may ask, why now? We don't have quantum computers now. So why we need to use the PQC when we do not have the quantum computers? So there is a type of attack that you can record our current information and then break them when you have a large scale of the quantum computers. So for most of the use cases, one of the example is the governmental information, we need actually to keep them secret for decades. So we have to use the PQC as soon as possible. What is included in this standardization? The first one is the key exchange mechanism, which is a replacement for Diffie-Hellman approach. And another one is the dilithium digital signature algorithm, a replacement of RSA or ECDSA. So what is the motivation of our work? There is no doubt that we have to use the PQC as soon as possible. And hardware accelerator plays a critical role here because they can lead to the better performance, efficiency, and more importantly, they achieve better SCA protection, or they can be more secure. The other things is you have actually Calyptra as a root of trust engine, and we want to make it quantum safe. So this is our other motivation to do this job. But there are still actually some challenges here. The PQC, as I mentioned, is not finalized yet, and there are actually some ongoing changes and updates on the protocols. So we have to wait until we have the final, we have to make our architecture and our design exactly compatible with what needs will be standardized. The other things is we cannot reuse what we have from the ECC and RSA from our previous design because they are completely different. They have different arithmetic, different operation, and we cannot reuse none of those operations. The other things is we cannot reuse what we have already as open source design from the academia and other things, because in some cases they have increased the performance, but they leak the information. And there are, as I mentioned, there are lots of updates and changes in the protocol that makes actually those design non-reusable. The other things is there is a lack between the appropriate trade-off between the resources utilization and the performance. In the hardware design, there is always a trade-off how much we want to achieve the performance at the cost of the area utilization. So there is still actually a gap here. So based on that, we introduced Adam's Bridge Accelerator. This design targets the dilithium digital signature algorithm right now, and then we will add the Kyber key exchange mechanism to that. We target two different performance levels, one for the embedded architecture, the other one for the standalone architecture or high performance design. This design would be a unified architecture that supports all the required operations for a crypto system, which is key generation, signature generation, and also signature verification. This design would be a pure hardware architecture and hands-off interaction, which means that there is no hardware-software co-design or firmware hardware interaction in between, and everything will be happened in the hardware. And also we embed different side channel countermeasures to protect our architecture against information leakage. So what is actually dilithium based on? This actually slide shows the mathematical background of the dilithium. So suppose that A is your public key and S is your secret key, and the multiplication between them results in T. And having A and T in the first equation, you can easily find what is the S. So if you add E as a noise to the product of A and S, you can change this equation to be a quantum safe problem. So considering the second equation here, this equation has more than one answer, and having actually a large dimension for each of these vectors and matrices, the quantum computer cannot find the exact solution for that. So it would be quantum safe. However, there are some challenges to implement these equations. One of them is there are lots of randomness here. Each of elements of these vectors and matrices needs to be filled by random values, and we need actually a random generator here. And the other things is there are lots of these equations, and we need several polynomial multiplication or vector by vector multiplication. So we need actually ketchup, which is a SHA-3 hashing algorithm, to provide us the required randomness, and then we use different samplers to fill these vectors, and also we use NTT to accelerate our polynomial multiplication. From the side channel point of view, all of our design are constant time, and there is no secret dependence branching or memory access during the computation to avoid timing and simple power analysis attacks. For the DPA attack, we consider embedding different masking countermeasures to our design, which of course would be at the cost of more area and also latency. And also our design would be constant time, and we add control flow countermeasures to protect our design against template attack. From the performance point of view, our design would be, in most of the cases, faster than classical or ECC design. But there is a main difference here. In the ECC or RSA, in the classical crypto, after having one signature, the results would be valid. But for the lattices, for the PQC algorithm, there are some validity check after the signing, and we have to pass all those validity check to make sure our signature is valid. And in most of the cases, we need the signature, the result is not actually pass all the validity check, and we need actually to redo the operation until we achieve the we pass all the checks. At that point, we can actually publish our results to the user. So the average number of these actually rounds is 3.85, which is still significantly better than ECC. But again, in the worst case scenario, P99.99 success, we need 31 rounds of the signing. We need to repeat signing 31 times. And this is still comparable with what we have in the ECC 384 security level, which means that PQC algorithm is faster than, in most of the cases, it's faster than ECC and classical crypto. And in the worst case scenario, they are still comparable with the same performance level with the classical crypto. So to conclude, we need actually the PQC, and we have to use it in our product, in our actually design. Based on that, we actually proposed Adam's Bridge Accelerator to implement the dilithium for the cloud infrastructure. With that design, we can actually tackle the different challenges in the PQC implementation, including the performance, complexity, and SCA, or side channel attack protection. And we actually developed a highly parallel and pipeline architecture to accelerate our design. As a next step, we use this design, the embedded version of the Adams Bridge, the Calyptra, and that's actually the place that everyone can contribute to this project and use it in their product. Thank you.